Can you hear me at the back? All right, so we had talked about these things in the last class. So we had talked about all these things and क्या बोले आप? This was fine, I think, right? We are not going into the mathematical details of lattices. What we are simply saying are these things, and this idea was pretty well understood, I think, in the last class itself. So now we were talking about graph search. Many of you had suggested better ways of doing things when we were doing BFS and so on. So how would you detect, how would you draw this as a search tree? How would you draw the corresponding search tree for this state space graph? Start from A. Now from A to B you have two paths. Okay. Then again from B to C you have. So if you were to just draw until here, how will your tree look like? A at the root, then you have B, and then you have 4 C's, right? So there are, if all these have different weights, then you have potentially 4 ways to reach to C. So that's how you see it here. Here. If this continues like this, how is my number of nodes in this tree increasing? 2 to the power n. So n states there, and in this side you are having exponentially many 2 to the power n. So this is really bad. So in tree search we are doing a lot of extra work because we are not able to detect the repeated states. And you remember अपन जब ये कर रहे थे example, many of you had pointed that out. Remember this? Many of you had said, sir, वो करेंगे क्यों? Because I've already been there. So we are doing that same thing now. So in BFS, for example, we shouldn't bother expanding the circled nodes. Why? Now it is trivial for you to answer. So E you have already explored. What about A? What about A? You've done it before? You've already done it here. Okay. P and Q already done here. So if you have done something in a level above yourself, you don't need to repeat that for BFS. Right? This is true for BFS and similarly for DFS and other algorithms too. So idea is to never expand a state twice. And how to implement? So let me get this whole slide first. Right. Idea is to never expand a state twice. That's why you guys essentially suggested. So nothing new in that. How to implement this? Tree search plus set of expanded states. That's a closed set. Expand the search tree node by node. Before expanding a node, check to make sure its state has never been expanded before. If not new, skip it. If new, add to the closed set. What is happening in all these 4 statements? ये सब आप सोच चुके हो. So don't read it here. You know how to make sure that you don't repeat. If you have been to one node, if you have been to one state, then keep it mark in some sense. So if not new, skip it, and if new, add it to the closed set. Expand the search tree node by node. That's what we have been doing. Before expanding a node, check to make sure that its state has never been expanded before. If you have expanded it, then don't do it. If it is new, then you have to put it inside the set. So what is this set in our case? This is our fringe now, right? So now, अभी तक हमने क्या किया था? अभी तक we had not put any restrictions on how we are putting things inside a fringe. Everybody was a candidate. Now what we are saying, you have to be cautious about what do you put inside the fringe. Okay. So here there is a note, it says store the closed set as a set, not as a list. Okay. Can a graph search wreck completeness? Now we are asking something important. So tree search we have seen for A star, it was, so A star was complete and optimal. Now we are changing our rules, so can we say that it is still complete and what was the other thing, optimal? Attendance शुरू कर दो, so that last में अपनी एक भी मिनट वेस्ट ना हो. Graph search के अंदर, yes, yes. So the question that we are asking is, if we use graph search for whichever algorithm you were using, right? So let's say use UCS, A star, whatever. If you start using graph search instead of tree search, will completeness still hold or not? Now, at this point of the course, we are specifically interested about which algorithm? A star. BFS, DFS are all gone. We care more about A star now. So now we can boil down this question to specifically this thing. Can graph search wreck completeness of A star? Okay. We'll see why not. So these two things are of interest to us. We want to use A star. What are the changes we are doing? What are the changes we are doing compared to what we had before? So now you have to keep track of those states which have already expanded, right? I don't want to expand them anymore. Anything that can go wrong? Is there any correctness issue, by the way, in this? See, as a computer scientist, when you design an algorithm, the first thing of interest is correctness. Will it break the algorithm? Will it break the algorithm? What does breaking algorithm mean in this case? Optimal, nahi. Completeness is breaking the algorithm. So if your completeness breaks, what does it mean? There is a goal, but still your algorithm is saying that there is no goal. I don't want this. This is a correctness issue, right? And optimality issues are of course there. So these two are important questions that we need to answer. A star graph search gone wrong. Until now we have done A star tree search. Now, if this is the graph, so let us see this step by step now. This is the things given to us. H, our heuristic is given to us. What do we do next? So we start from S. 0 plus 2 now everybody understands? Alright. What will be the next? A or B? So here you have 1 plus 4 and here you have 1 plus 1. Done? Next. B can take me to C and A can take me to C. Okay? And which of these two will I do? So shall I go slow? 1 second. So we were here. Fine. Until here we are in sync. Fine. Now you go to C of 3 plus 1. 3 plus 1. What do I do next? See, why am I not going this way? So this is 4 plus 1, 5, and I have candidates that have this value less than 5. So this is less than 5. Done. What do I do next? C expand. So we expand C and we see A and G are in my fringe now. We have seen it before that you cannot stop when you NQ. You have to stop when you DQ a goal. So right now we have this in fringe. By the way, just by looking at this, which one is the best path? SACG. Right, this is 2 here. Okay. So I should get actually this one. What happened here? A is expanded. So I get C. Okay. I am at C. So this one. What went wrong here? Exactly. So if you encounter C here in graph search, what graph search says? I've been to C, I won't expand it. So I won't expand any of it here. That means I have reached goal. So I'll declare this one as the goal rather than SACG. I will declare SBCG as goal. Everybody sees this problem? Okay? I don't get this. Okay? Right. Right. It is admissible. Admissible की कंडीशन क्या थी अपने? Okay? Now, but what you are saying is right. Okay? So what is the problem here? The problem here is actually indeed this guy. So admissibility was a requirement for tree search. If, so we said that A star is optimal given what? A star is optimal given H is admissible. Here we need something similar. So A star so let me just give this whole slide first. They've started doing something. Okay. Right. Consistency of heuristics. So when you are doing A star graph search, admissibility alone is no longer sufficient. Somewhere it is written. Main idea is that estimated heuristic cost should be less than the actual cost. As you already pointed out, H was 4 in that case. It was admissible but not really sufficient. So what you are supposed to do is, admissibility is heuristic cost is less than actual cost to goal. And actual cost to goal was 1 plus 1 plus 3, 5. All H were less than 5. So they were all admissible. But if I go back there, maybe all of you will appreciate this. What is wrong with this H equal to 4 here? See, H equal to 2, H equal to 1, 1 still makes sense. What is problem in this segment? Actual cost to reach there is 1. But you have a heuristic that says 4. So there is some issue with this, right? Now, what is this consistency property saying? Consistency property says, so admissibility says cost from start to goal. All H should be less than this number. Consistency says don't just talk about goal. For every arc, this thing should hold. The cost to reach from S to A should not be more than 1 for any heuristic. Okay? So you make consistent heuristics now and you call them consistent. That's it. So not the greatest of the names. Okay? Admissibility is heuristic cost less than actual cost to goal. ये चीज लिख लो. Important चीज है, मैं पूछूंगा and then फिर डन हो जाएगा मामला. आपको लगेगा समझ में आया था? ओके, consistencies heuristic arc cost has to be less than actual cost for each arc. If you remember this, you are done. Admissibility means all heuristic values should be less than S to G, that's it. Consistency means I don't care from S to G. I care if you are going from A to B, then heuristic value has to be lesser than the actual cost from A to B. Okay, so consistency is heuristic arc cost has to be less than actual cost for each arc. Does this also imply admissibility? Does this imply admissibility? कैसे? No? कैसे?
गोल की ज्यादा हो सकती है ओवरऑल कॉस्ट. अगर A to B जा रहा हूँ उसका एक्चुअल कॉस्ट 1 है और उसका एक्सपर्ट 4 है. इन दैट केस इट्स नॉट कंसिस्टेंट. बट अगर मेरा गोल से वो कम है तो इन दैट केस इट्स एडमिसिबल. गोल का अगर 7 है और अपना एज 4 है so it's admissible but it's not consistent.
Anyone else has a contrary view? Does consistency imply admissibility? वापिस समझाओगे मेरे को? समझ में कम आ रहा है मेरे को. So admissibility implies, sorry, consistency implies admissibility. I am not doing further discussion on that. Now, okay, so now A to C, H equal to 1, HA minus HC. Remember this? This is the definition of your consistency. HA minus HC has to be less than cost from A to C. Done? And now you know. So F value along the path never decreases. So HA is less than cost to A plus, basically just rearranging this. A star graph search is optimal if your H is consistent. So we have fixed everything that we had to fix. So A star graph search is also optimal, and like many of you suggested कि सर अपन बार बार क्यों जा रहे हैं same state पे, right? That thing is now gone. You don't need to visit a state more than once. All right, so you can do that same thing again that we had done in the class. Okay, this is the right thing now. है ना? This is what we were talking about. Right. I will leave this proof as a homework. The proof is same as before, a couple of facts are changing. You can look at that. चलो, नहीं तुम जाओ. हाँ, कितने लोग ऑनेस्टली बोल रहे हो कि भाई नहीं हो पारी क्लास? अच्छा, कितने लोग ये हमेशा ही बोलते इनमें से? So then I don't see many. हाँ, ऑल राइट. तो फिर क्या करें बताओ यार, ये तो अगर नहीं चलेगी तो भैया रीइंफोर्समेंट लर्निंग पे तुम लोग खुद बोलोगे सर रीइंफोर्समेंट लर्निंग कब करेंगे फिर अपन? उनको इंट्रोड्यूस तो कर दिया था, इस स्पीड से तो अपन इंट्रोड्यूस भी नहीं कर पाएंगे. नहीं वैसे देखो, सीनियर्स को छोड़ो, इनकी अच्छी खासी हुई थी. एमडीपीज मीन्स रीइंफोर्समेंट लर्निंग. तो क्या करना है, कंटिन्यू करें नहीं करें? हाँ, तो प्रोजेक्ट डिस्कशन के लिए यहाँ नहीं बैठना तुमको. अब 40, अब 20 मिनट हो गए हैं, 20-25 मिनट और सही यार. हाँ, चलो चलो अब अपन कंटिन्यू करते हैं. All right, so we start with a different topic now. Search is done for us. I mean, not really, but we have had a very good tool with us now. देखो देखो ये सब is adding to the extra time. So we start with constraint satisfaction problems, in short called CSPs. Again, these slides are from CS 188. All right, so what is a search for? Assumptions about the world, a single agent, deterministic actions, fully observed state and discrete state space. ये समझाओ मेरे को एक बार देखें. What does this mean? This is what we had assumed throughout last whatever number of lectures we have had. What does it mean to say a single agent? But you were searching, given a state space, you were searching for something. So it was just basically what we want to say is it's not a two-player game or more. Right? Pac-Man is not a two-player game, right? It's a single-player game. Deterministic actions means you could make a tree and you were definite that in a state, if you take action south, you are going to end up in south. Okay? It was with probability 1. So deterministic actions. Fully observed, what does this mean? You could make this whole tree all the way from starting to the end, goal state. Discrete state space, there are transitions. So there is something like state 1 and state 2. Not things like where things are continuous. Okay? So planning sequences of actions. Planning is a sequences of actions, and if you see these days, these two terms are pretty hot. एक तो ये कि we want agents, and then whether those agents can plan or not. So sequences of actions is planning. The path to the goal is the important thing. Paths have various cost and depths. Heuristics give us problem specific guidance. ये सब अपन देख चुके हैं. Okay? Heuristic वो अपने एज की बात हो रही है यहाँ पे. Paths have various cost and depths, कोई बड़ी बात नहीं है. And path to the goal is the, because that is what we are looking for. This is the planning problem. You are looking for path in case of identification, assignment to variables. The goal itself is important and not the path. All paths at the same depth for some formulations. We'll see what does it mean. CSPs are a specialized class of identification problems, which are this one. Okay, so we have talked about A star in general, and now we are going to shrink our applications. Okay, constraint satisfaction problems. So I'll come back to this slide. Just give me this. So let's say if I just give you this empty map of Australia, no colored, nothing. Our goal is to color it. Our goal, so you have three colors, RGB. Our goal is to color this country such that no two adjacent states get the same color. Okay, so is this okay? This is fine. Now if I give you empty this, you start coloring. Okay, goal itself is important, not the path. Is that correct in this case? What we care about is a correct coloring. I don't care what was the path taken to that. All paths at the same depth. What does this mean now? You start from, what will be the start state? All empty. What will happen at the next level? There are 7 states. So what will happen at the next level? How many children to this state, start state? 7. What will happen at the next state? 1 colored. 1 will be colored no matter which color you are putting to whom. But total 3 colors. So how many states at the first level? After root? I have 7 states. Each one I can color green. Single. I have 7 states. Each one I can color red. I have 7 states. Each one I can color blue. So how many children of the root node? 21. Okay. Now what will happen at level 7? All colored? So CSPs are a specialized class of all paths at the same depth, right? All paths at the same depth for some formulations. So all valid colorings, they will be at which level? They will be at 7th level. You can't have valid colorings at 6th, 5th or 4th level. Does this make sense? Chalo, let me ask anyone randomly. Batao. So, can you just tell me the topic we are talking about? Huh? What is search for? Nice. क्या बोल रहे हो? छोड़ो. What we are trying to solve right now is which problem? Constraint satisfaction problem. कर क्या रहे हैं उसमें? Let me not go into this jargon right now. Problem is this. यार ये सच में क्लास नहीं हो रही है. वीडियो में तो नहीं आ रही डिस्टरबेंस. खैर, ऑल राइट, देखो फटाफट कंप्लीट कर लेते हैं फिर निकलते हैं. आई डोंट वांट टू टॉर्चर यू फॉर लॉन्ग. 1 2 3 4 5 6 7. ओके, ये स्टेट्स के नाम के वेरिएबल्स हैं. व्हाट डू यू थिंक हाउ शुड फॉर्मलाइज इट लेटर? व्हाट वैल्यूज कैन दिस वेरिएबल टेक? व्हाट वैल्यूज कैन दिस वेरिएबल टेक? 3 RGB. What values can this variable take? नहीं, एकदम ओपन रहो अभी. 3. All of these they can take 3 values. You will bring in constraints to say that these colorings are illegal. But unless those constraints come to you, all each of them can be assigned 3 colors. Okay? So domains, you have already told me what are the domains for these variables? RGB. Okay. Constraints now come. Adjacent regions must have different colors. So implicit constraint would be, for example, WA cannot be equal to NT. Explicit would be WA and NT ordered thing should be either in red green or red blue or green blue, right? And does it matter if I make it green red? It will, right? Because WA becomes green and this becomes red. Okay? Solutions are assignments satisfying all constraints. For example, this is a solution. So basically this one, this is a solution. Okay. Now let me go back to this. So standard last slide and we go. Okay. Standard search problems. State is a black box. Goal test can be any function over states. Successor function can also be anything. What does it mean here? Now in CSPs we are specializing things. A special subset of search problems. State is identified by variables xi with values from a domain D. We have seen, so what are the variables in our problem? Name of the states. What was domain D? Colors that could be assigned to them. Goal test is a set of constraints. What was this constraint in our case? Adjacent nodes should not have the same color. Specifying allowable combinations of values for subsets of variables. And simple example of formal representation language, and we have seen. Okay, so I think that is it for today. And right, so this is it for today. अटेंडेंस कितने लोगों? एक सेकेंड. कितने?
कितनी है सर एक्स्ट्रा?
चलो कितने? ऑल राइट, दिस इज फाइन. हाँ, यार जनता पढ़ने को तो तैयार नहीं है.
पॉइंट
क्या हुआ?
सर यहाँ पे किसी ने 20
ठीक है, इसमें तो I was looking for a video kind of thing. And you do think आप लोग ग्रुप डिस्कशन चलाओगे क्या करेंगे?
वो कोई पार्टिसिपेट नहीं करेगा, कोई इतना नहीं करेगा पार्टिसिपेट।
देखो, अगर कोई पार्टिसिपेट नहीं कर रहा है ना, then this already means.
वो मतलब ये लोग ऐसे हो जाते हो, फिर वो कोई बात नहीं होगा।
अरे बोलो, मैं फैकल्टी को बोल रही हूँ, बोलो. नहीं, आप लोग बात करो. I'm not willing to penalize you in any way. ठीक है? But I need to figure out a way. क्योंकि I have something in mind, but I won't say anything until you guys come up with some idea.
तो आप ही कर दो ना, तो सोच लो। कि वो हम कर सकते हैं। 5 मार्क्स का ही होना है।
That's what I'm thinking. But I want to give that choice before I start checking. जिन्हों को इतना कॉन्फिडेंस है कि वो सही करके आए हैं, वो बोलें कि सर मेरा तो अभी चेक कर. और ऐसा करने वाला कोई नहीं था. मैंने पूछा, कुछ लोग बिल्कुल मिले थे रास्ते में. मैंने कहा जिसको चॉइस चाहिए, मैं व्हाट आई वोंट अलाउ इज द फॉलोइंग, कि अभी तो बोल दिया हाँ सर अलाउ कर लो, 5 में से मैंने एक पकड़ा दिया. देन यू कम लेटर कि नहीं नहीं सर प्लीज प्लीज प्लीज, आपने कहा कोई
वो तो डिसएग्री और एग्री वाले का ही होता है।
एग्जैक्टली. हाँ, सो इधर आई कैन डू दिस थिंग कि जस्ट मेक इट इक्वल टू 10%.
हमारे पोल पे वो लोग रिप्लाई नहीं करते कि
आप कुछ बोल
सर
आप एक बार ना टेक्स्ट तो कर दो।
हाँ ठीक है. इफ आई अनदर थिंग आई कैन डू इज इसको जस्ट 10% कर दो, व्हिच विल एक्चुअली मेक सेंस. यार 8 लेक्चर में मिशन होता है क्या?
तो उन्होंने सर वही तो डाला था हमने पोल पे कि 10 मार्क्स का मिड टर्म कर देते 35 मार्क्स का वो
मिड टर्म टू पर जो बच्चे बोल रहे हैं कि नहीं फिर ज़्यादा हो जाएगा इसमें, ये वो अगर जो आएगा हो जाएगा, ऐसे कर रहे हैं। फिर वो बोल रहे कि ठीक है वैल्यूएट कर लो, कोई बोल रहे हैं कि नहीं करते हैं। वो समझ में आ रहा ना।
तो पर 30 लोग ऐसे हैं कि जो बोल रहे हैं लगता है नहीं वैल्यू
चलेगा।
करना चाहिए सब मोर देन हाफ.
आई फाइंड दैट मोर रेशनल. वो चॉइस देना ना, वो chaos है. चॉइस देना chaos है कि अभी मैं उनकी कॉपी चेक कर दूँ कि वो.
हाँ है।
The only problem I find in this whole thing is कि जिन लोगों ने सेकंड क्वेश्चन करने के चक्कर में फर्स्ट को कम टाइम दिया, इस वजह से आई एम होल्डिंग अप बिकॉज.
सर ऐसा कोई नहीं सर, एक दो अच्छे होंगे सर.
हाँ राइट दैट मेक्स सेंस.